Today, we're going to crack the code on a classic physics puzzle. Now, this isn't just some textbook problem. Think of it more like we're predicting the future. We're going to use the fundamental laws of the universe to figure out exactly what happens in a physical system. So let's dive right in.
So, here's the mystery we're going to unravel. The setup looks simple, right? But it's packed with physics. We've got a block on a table, tied by a rope to another block just hanging off the edge. So, when we let go, what's going to happen? How fast is this thing going to move? How much strain is actually on that rope? And, to be really specific, where will that block be after exactly 1.5 seconds? Let's figure it out.
All right, first things first. Before we can predict anything, we got to know who the players are in this little drama. We need to understand exactly what we're working with.
Okay, so here's the info we have. The block on the table, M1, has a mass of 6 kilograms. The one hanging, M2, is a bit lighter, at 3 kilograms. And then there's the friction between the table and that first block. It's represented by this coefficient of 0.20. You can just think of that as a number that tells you how grabby or sticky that surface really is. Believe it or not, these three numbers are all we need to solve the whole thing. Okay, now for the really cool part. Physics, when you boil it all down, is all about forces, these invisible pushes and pulls that make everything happen. So to understand the motion here, we need to map out this epic tug-of-war that's about to go down. Our system has two main characters, right? Block M1 on the table and block M2 just hanging there. And they're in totally different situations. Block M1 has to deal with gravity pulling it down, the table pushing back up, the rope yanking it sideways, and friction trying to stop the whole party. Meanwhile, block M2 has a simpler life. It's just stuck in a two-way battle between gravity pulling it down and the rope pulling it up.
So how do we tackle this without getting confused? Well, we're going to use a classic physics move, divide and conquer. We'll look at each block totally separately, and we'll draw what's called a free body diagram to map out every single force acting on it. Let's start with the block on the table, M1.
All right, let's break it down for our sliding block. First, you've got gravity, of course, pulling it straight down. But the table pushes back up with an equal and opposite force we call the normal force. It's normal just because it's perpendicular to the surface. Then, the rope pulls it to the right. That's the tension. And finally, friction, the villain of our story, is pulling to the left, resisting the motion. It's a real four-way fight. Now the hanging block, M2. Its story is way simpler. It only has two forces to worry about. You've got gravity pulling it down, and that's really the engine driving this whole system. And you've got the rope's tension pulling it up. That tension is the critical link that connects everything together.
So we've got our force map. Now it's time to turn that map into an actual number. What we're looking for is the system's acceleration. Basically, how quickly this whole thing is going to pick up speed. This is the first big unknown we need to solve for.
And to do that, we need the master key, Newton's second law of motion. It just says that the net, or total force on an object, is equal to its mass times its acceleration. F net equals ma. It looks simple, but this little equation is incredibly powerful. It's the bridge that connects all those forces we just mapped out to the actual motion we're trying to predict.
So, if we look at the whole system at once, what's the big picture? Think of it like a car. The gravity pulling down on that hanging block, M2, that's your engine, pushing everything forward. And the friction on the block on the table, M1, that's the brake, trying to slow it all down. So the engine force minus the braking force equals the total mass of the car, both blocks together, times its acceleration. And after we plug in all our numbers and do the math, what do we get? Boom! The system accelerates at 1.96 meters per second squared. What that means is, for every single second that goes by, the speed of the blocks will increase by almost 2 meters per second. The first piece of our puzzle is solved.
Okay, so we know how fast the whole thing's moving. But what about that rope connecting the two blocks? What's the actual strain on it? You know, the tension? Finding that is our next crucial step.
The trick here is to zoom back in and just look at one of the blocks. Let's pick the hanging block, M2, because it's a bit simpler. For that block, gravity is pulling down and tension is pulling up. Since it's accelerating downwards, we know gravity has to be pulling harder than the tension. In fact, that exact difference in force is what's causing a 3-kilogram mass to accelerate at the rate we just found. So we run the numbers and there it is. The tension in that rope is 23.52 newtons. That's our scientific unit of force. And check this out. That number is less than the force of gravity pulling down on block 2, And that makes perfect sense, right? That's why the block is accelerating downwards in the first place. Gravity is winning the tug-of-war.
All right, we have our acceleration and we have the tension. We know the how and the why of the motion. Now, for the grand finale, let's actually predict the future. We can use these numbers to pinpoint exactly where that sliding block will be at a specific moment in time. And for this, we need to pull one last tool out of our physics toolbox, a kinematic equation. Now, it might look a little intimidating, but it's really just a recipe. It lets us calculate distance as long as we know the starting speed, the time, and, this is the important part, that acceleration we just worked so hard to find.
So we know the system starts from a dead stop, which means its initial velocity is just 0. That makes the first part of the equation easy. It just goes away. Then we plug in our acceleration, 1.96, and the time we care about, 1.5 seconds. The stage is set for our final answer.
And voila! In exactly 1.5 seconds, the sliding block will have moved 2.21 meters. How cool is that? We've just successfully predicted the future using nothing but a little bit of math and the laws of physics.
So, let's take a step back. What did we actually accomplish here? Yeah, we found a few numbers, which is cool. But what's really important is the powerful method we use to understand what's going on in the physical world. Let's recap what we figured out.
Here's the whole story, told by the numbers. An acceleration of 1.96 meters per second squared, a rope tension of 23.52 newtons, and a final predicted distance of 2.21 meters. We started with a pretty simple question, what happens next? And we ended up with a super precise quantitative answer.
And honestly, this is the real takeaway. The power of physics isn't just about memorizing formulas. It's a way of thinking. We took a complicated situation, we broke it down into its simplest parts, the forces, and we built a mathematical model that perfectly predicts what it's going to do. And that process, you can apply that to all sorts of other problems.
We saw what happens when the driving force, gravity, wins the tug-of-war. But what if it didn't? What if friction was so strong that it could just hold everything in place? What if it won the tug-of-war before the fight even began? Well, that brings in a whole new character called static friction, and a whole new puzzle to solve. But that's a story for another explainer.